A very warm welcome to the lecture on the subject of wavelets and multi-rate digital signal processing. Let us spend a minute on what we had done in the previous lecture. We had looked at the two-band filter bank in the previous lecture, and we had written down a set of conditions based on what happens when you go past a downsampler and an upsampler in the Z domain. So, let us put down the conditions once again, or let us in effect put down the relation between the input and the output in the Z domain, where it is valid to use the Z domain, which is true in many circumstances. So, let us summarize what we had derived the last time. We said to a two channel filter bank, input x n, its Z transform. Now, I will use this script Z to denote the Z transform, capital X Z, output y n with Z transform, capital Y Z. Now, incidentally, we suppress the regions of convergence. So, we do not explicitly mention the regions of convergence. Analysis side, H 0 Z, the so called low pass filter, and H 1 Z, the high pass filter. Synthesis side, G 0 Z, low pass filter, G 1 Z, high pass filter. So, this is the circumstance. Of course, you know where the downsamplers and upsamplers are. The relation between y z and x z is as follows. We have y z is tau 0 z x z plus tau 1 z x of minus z. And recall that we had called this the alias term, and therefore, tau 1 z was called the alias system function. I put system function in inverted commas. I must emphasize here, when there is an alias term, the word system function is actually a misnomer. One should not use the term system function, because the system is not linear and shift invariant. On the other hand, if tau 1 z is 0, the system becomes linear and shift invariant. So, this is something that we must now take note of. Tau 1 z equal to 0 is essentially what is called the condition for alias cancellation. And we note the system becomes linear and shift invariant. Now, we had looked at one possibility under which tau 1 z could be 0, and we had said the most general possibility can be accommodated by what is called a cancelling term R z. Let us put that down again. We said tau 1 z is essentially the function or the expression half g 0 z h 0 minus z plus g 1 z h 1 minus z. And tau 1 z equal to 0 means essentially that g 0 z by g 1 z must be minus h 1 of minus z divided by h 0 of minus z. And the simple case is equate the numerator and denominator. So, equate, if you equate the numerator, you get g 0 z is plus minus h 1 minus z and g 1 z is correspondingly minus or respectively plus h 0 minus z. We had also interpreted these expressions in the ideal case. If h 0 z for example, was the ideal low pass filter, then this would become an ideal high pass filter as we expect, and if h 1 is the ideal high pass filter, this would become the ideal low pass filter, all with a cutoff of pi by 2. So, in that sense, we have a neat interpretation for the ideal case. Even if the filter is not ideal, we have a reasonable interpretation, in the sense that we could always take this to be a non-ideal low pass filter with a cutoff of pi by 2, and this would again become a reasonably close filter, high pass with cutoff pi by 2, and vice versa for this. If this is a high pass filter with cutoff pi by 2, then this becomes a reasonable low pass filter with cutoff pi by 2. Whatever it be, let us now of course consider the second condition. You see, this is alias cancellation. With alias cancellation, we are assuming that there is linearity and shift invariance in the system. There is a linear shift invariant system there. What is the system function then? If tau 1 z is equal to 0, then you have y z is equal to tau 0 z x z, and we are saying effectively that tau 0 z is the system function in the true sense. So, this is an LSI system with system function tau 0 z. Now, you see, one of the things that one needs to worry about is, what should tau 0 z be? Tau 0 z is also modifying experience for the input, and ultimately we want decomposition and reconstruction. So, in reconstruction, we want x z to be almost the same as y z, if not quite, if not identical, at least there must be tolerable changes. What are these tolerable changes that we can allow? Or more appropriately, what can we and what should we tolerate here? That is what we need to think about. What can we and what should we tolerate? Well, if we are talking about time systems, then we have to tolerate a delay. First, let me explain this intuitively, and then let me put it down mathematically. The filter does some processing. It takes some time to process at the analysis side and at the synthesis side. Now, you need finite time to process at the analysis side, you need finite time to reconstruct at the synthesis side. So, if you want no other change between the input and the output, at least you have to accept the change of a delay to allow for some time to process. So, if we do not want any other change, at least we should allow for a term of the form z to the power minus d in tau naught z. The other thing that we do not mind allowing is an overall multiplicative constant. After all, we do not mind if the whole input sequence is multiplied by some constant c, because we can always multiply by 1 by c at the output. It is a simple operation to do, a simple amplifier or attenuator. That is not very difficult to do. So, we do not mind if the whole LSI system that we have here after alias cancellation multiplies by a constant and delays by d, and that is exactly what we shall now put down mathematically. So, we are saying in a perfect reconstruction system, we should say we allow tau 0 z to be of the form some constant times z raised to the power minus d is a constant. Ideally, we would have liked tau 0 z equal to 1 for all z, essentially an identity system. Now, that would, as I explained before, make the system non-causal. So, this allowance of z raised to the power minus d, of course, d is positive here, is allowed because of causality. Now, we will take the example again, as I said, of the Haar MRA and the filter bank corresponding to the Haar MRA. Once again, we will see if we understand the Haar case, we understand a lot of things at once. So, let us put down the filters for the Haar case.